Hello and welcome to this film, which is all about hydrolysis reactions, and in particular we're going to be looking at the hydrolysis of esters and amides, two of the functional groups that we've seen so far. And hopefully by the end of this film you'll be able to predict what you're going to form when you hydrolyse an ester, and you'll have some understanding of why the conditions that you use when you hydrolyse it will often mean that the products we make are not the same as the reactants we would have used to produce that ester in the first place. Now, that might seem a little bit obscure at the moment, but hopefully it will make sense soon. And then once we've learned about that, we'll go applying these same principles to the hydrolysis of amides so that we can see that these two reactions are barely different at all. Okay, so let's just remind ourselves of what an ester looks like. Here's a molecule that's got an ester functional group in it. And you might remember what we said when we were looking at esterification reactions. So when we were making these molecules, we would take a carboxylic acid. So here's a carboxylic acid, which would normally have an OH group attached to it. And we'd combine that carboxylic acid with an alcohol. And as the alcohol lost its H and the carboxylic acid lost its OH, we'd produce some water, and that's why it was called a condensation reaction. Now, you might not be surprised to hear that if we produce water when we make one of these esters, we might need to put water back in if we want to break it up. So what we're going to look at now is two different ways that you might use water to break these things up. Now, first of all, let's do it in acidic conditions. So we're heating this ester with dilute sulfuric acid. And you might be thinking, well, hang on a minute, wasn't this a reaction with water? Well, yes, it is. There's lots of water here, but we have to have a catalyst. So that's what the sulfuric acid is doing there. However, if you were going to write an equation for this, you wouldn't be trying to put the sulfuric acid in. You'd be thinking to yourself, well, this is just hydrolysis. It's a reaction with water. Okay, now what happens when you put the water back in? Well, let's think about where the alcohol and the acid would be. Okay, so we're going to put the OH back onto the acid. We're going to put the H back onto the alcohol. So there's our water molecule that we've reinserted, and we're going to form a carboxylic acid product and an alcohol. And in this case, it's going to be propanol, CH3, CH2, CH2, OH, and the carboxylic acid would be ethanoic acid, because we've got two carbons here. Okay? So there are our products, and yes, we form an acid. And you might be looking at that and thinking, well, but they're exactly the two things that I would put together to make this ester. And earlier you were saying that often we wouldn't make the same two things as we would have used to make this thing. And that's because usually you wouldn't carry out this hydrolysis under acidic conditions. And the reason for that is because the things that you make can so easily recombine to produce the thing that you're trying to break down. Okay, so what we would quite like to do is to carry out this hydrolysis in a way that doesn't produce the same two things, so that they can't just go ahead and react back and form the ester again. So let's see what happens if we do this under basic conditions. Right, this time we're using sodium hydroxide as our catalyst. Now, again, this is realistically a reaction with water, but it's probably easier to think of it as a reaction with hydroxide ions from the sodium hydroxide. So this time we're going to break up the ester in the usual way, but instead of having H2O to put back in, we've only got one H and one O. So we're going to give the alcohol its hydrogen back, but we haven't got enough hydrogen to give the carboxylic acid its hydrogen back. So we're just going to give it the O minus that's left over. So we've got an H and an O minus. Now what are the products going to be? Well, we're still going to form the same alcohol. Nothing's changed there. We're still going to form propanol here, right? But this time we're going to form the salt of the carboxylic acid. So we're going to form not ethanoic acid, but the ethanoate ion. Okay? And I suppose you could say that if we use sodium hydroxide, well, there's going to be a sodium ion left over to form this ionic substance. Okay? So No acid is formed this time, but the salt of the carboxylic acid. And the great thing about that is that the salt of a carboxylic acid won't react with an alcohol to produce an ester. They just can't do it. Okay, so this is a preferred way of hydrolyzing esters because you don't get the reversible reaction happening. Okay, so having looked at those things, let's look at what would happen if we broke down or hydrolyzed an amide. And we're going to start, like we did before, by looking at what we'd use to make an amide. So first of all, here is our amide functional group. What would we use to make it? Well, this bit here looks like a carboxylic acid that has lost its OH. So we could use a carboxylic acid, and if we gave an H back to this nitrogen, then this amide could be made by using ethanoic acid and ammonia. Okay? So, having considered what this amide is made out of, let's think about what's going to happen if we break it down. Now, if we do it in acidic conditions, just like before, we've got H2O from our acid. We're going to break the amide bond. We're going to give the carboxylic acid its OH back, and we're going to give the amine part of the molecule, in this case it's ammonia, its H back. Okay, so we'll have broken this bond. We are forming an acid. So this shouldn't say no acid formed, but indeed an acid is formed. Okay, we've got this acid here, ethanoic acid and ammonia. Now, what would happen if we did it in basic conditions? Well, sodium hydroxide being used again, remember that this is a source of hydroxide ions. We're going to break this amide linkage here. We're going to give the carboxylic acid its oxygen back, but we don't have enough hydrogens to give it its hydrogen back. We're going to give the H back to the ammonia, and now we're not forming an acid. We're forming a salt of the acid just like we did before. Okay, so again we need to realize that the conditions that we carry out our hydrolysis under will affect what the products look like. So if we were writing an equation for this amide being heated with sodium hydroxide, the equation would look different to the equation when it was heated with sulfuric acid, even though the hydrolysis reaction is basically the same. It's still a reaction with water essentially, but here, because of the basic conditions, we form the salt of the carboxylic acid. Right, I suppose there was quite a few things covered there in a fairly short space of time. Hopefully you can use your knowledge of esterification reactions and what you've covered here to see how it is that we can predict what will form when we break an ester down or hydrolyze it, and you can see how the products are going to be different depending on whether we do it under acidic or basic conditions. Hopefully you can also see that where there was an ester linkage, you could swap that for an amide linkage and use very, very similar principles to predict the products of your reaction when you hydrolyze an amide. As usual, if any of it doesn't make sense or if you've got any comments to make, please feel free to come and see me or to post a comment on YouTube.